Okay, so welcome to the next lecture of chapter 3 in the course Basic Modeling of Biological Networks, and it's going to be about kinetic proofreading. So you may not realize it, but precision is a very important aspect of biological systems. And with precision I mean not making errors. So many biological circuits and many biological processes are involved in copying states. So for instance, DNA can be copied into other DNA during replication. DNA can act as a template for mRNA, mRNA acts as a template for protein, and many of these processes, information is copied into another chemical form, but the information content of course needs to be preserved. So that means that when we go from mRNA to protein, the right amino acids need to be incorporated into the growing peptide, and when we are copying DNA, it needs to be ensured that no errors are made. And but that turns out not to be trivial, because if you think about, say, an enzyme, the copying enzyme, and this copying enzyme can bind to a nucleotide or an amino acid. Okay, so let's say A is a nucleotide, so it could be a base in DNA, or it's a particular amino acid, right? And giving rise to the complex. But if we think about this explicitly, so we have the mRNA, the ribosome, and the piece of the protein that has already been produced. The ribosome is at a particular location on the mRNA, and now the right tRNA, right, with the right amino acid needs to bind. But the wrong mRNA, the wrong tRNA, so the wrong version, so with the wrong amino acid, in principle can also bind. But the other one will have a higher affinity for this state of the ribosome, because the ribosome is now, has in its active site, the A site in this particular case, that's what it's called, the corresponding amino acid sequence, sorry, the mRNA sequence that corresponds to this amino acid, but not to the other. But this doesn't mean that this one cannot bind that. It can equally well, of course, bind at that particular site, but with a lower affinity. So, also, the wrong complex can be formed. Now, typically, when this happens, this state of the ribosome and the mRNA, it's so short-lived that it quickly falls apart, okay? So if this is the right substrate, okay, then this route is more probable than that route, simply because the enzyme has a higher affinity for A, for the right substrate, than for B. And the affinity for the substrate is in all these template cases determined by the location of the enzyme on the template. So the template itself, the location where the enzyme is sitting, determines what the right molecule is that needs to be incorporated into the growing peptide. So at a different location it will be a different molecule for which the enzyme has the highest affinity. So that means that if B would be formed, so the wrong one, it will typically go in the reverse direction, fall off, instead of making the incorrect product. And the incorrect product is in this case the polypeptide that we started with, so that's hanging on the E, that is actually part of the complex E. And here you have E, so the enzyme plus the correct product. Okay. So we want to ensure somehow that this is the preferential route. Well, the other route also takes place, but we want to minimize its occurrence. And the first thing that we're going to be discussing is if we consider this situation and we can form the incorrect product versus the correct product. So then we can ask, what is the fraction of events, right? So what is the, let's call this the error fraction. Okay, so that is a rate of incorrect product formation over the rate of correct product formation. And clearly what we want this error rate, this error fraction, sorry, we want it to be 0. So it needs to be as small as possible. So if we consider this scenario, we can ask what would be an equation for this error fraction. Okay, so let's number our reactions now. So here we have K plus and K plus, and we were going to assume that the association rate constant for A and B to the enzyme is identical. So K plus for A and K plus for B are the same, but the difference lies in K minus. So K minus prime versus K minus. And there is also a catalytic rate constant, so this is where the product is formed. And they are allowed to differ between the two states. So that means that the rate of incorrect product formation is in fact K cat prime times EB, and the rate of correct product formation is times EA. Okay, so we need to look at this error fraction, of course, at a moment in time where this has become constant. So we don't want these concentrations to change as function of time. So our measure will be at steady state. So we need to know the steady state concentrations of EA and EB. So let's write the differential equation for EA, K plus times E times A, K minus times EA minus K cat times EA. So we're going to look at steady state. So you have all these steady state concentrations, and A is fixed. So what is EAS? It is K plus times ES times A minus K minus times plus K cat. Yeah? And if you do that for EB, right, you have the same K, take A times B. So you'll see that you have exactly the same structure of the equation. Right? So EB as K plus times AS times A times K minus prime plus K cat prime. Okay? So given the differential equation, you set it at steady state and you solve it for these unknown concentrations, and this we can substitute there. Right? And then we end up with K cat prime, K cat times EB. Sorry, this should be B, of course. EB. So you get KB times E times B, K minus prime, K cat prime. And this we have to divide by EA. So that's the same as multiplying by its inverse. So K minus plus K cat divided by K plus times E steady state times A. And so we can need to continue somewhere out on the board where there is room. So let's do that here. So our error fraction is k cat prime k cat times k minus plus k cat k minus prime plus k cat prime times k plus times es times b k plus times es plus a. So this equation is just exactly the same as that one. Alright, so now we can simplify it a bit. We can say, look, so first of all, for an honest comparison, right, so if we want to compare how probable this is versus that, we're going to assume that a equals b. Because otherwise we can always make the error fraction go in any direction by playing around with the b and a concentration. So we're going to, they're equal, okay, this disappears, that disappears. So then we are left with this. Okay, and we're also going to assume is that the rate with which the product is formed from this state is going to be the same for the correct and the incorrect product. So the only thing that is going to be different between these two scenarios is the fact that the off-rate constant will be higher in the case of the incorrect product relative to the correct product, such that indeed it's more probable to make the correct product versus the incorrect product. So we're also going to assume this to be constant. So then it turns out that we have this. Right? And so now they're equal. And now in so when is this the smallest, right? This is the smallest, so is minimal when k cat is a lot smaller than k minus and k minus prime, right? Because if it would be larger, it would approximate 1, right? And that is a high error fraction. So if this guy is greater than that one, right, then the minimal value of this guy of the error fraction is obtained when the k cat is very small relative to these two values. So then approximately the k cat equals k minus a minus prime. Yeah. Now if you do k minus prime divided by k plus, and you divide those both by k plus, then you get the ratio of affinities, the dissociation constant. So what turns out is error fraction, its minimal value under those assumptions equals the ratio of k minus divided k minus prime. So this rate constant divided by that rate constant. Now each of these rate constants divided by k plus gives the equilibrium constant. So let me show you that again. Right, so if we just consider E plus A gives EA, yeah, the rate of that reaction is k plus times E times A, k minus times EA. So the equilibrium constant, so the dissociation constant is defined like this. So this should be k minus divided by k plus. Yeah, so that is the dissociation constant. And the same for B, right? So then it's just B. And you will get B kp is is K minus prime divided by K plus. Okay, so that is what these affinity constants are here. Those are the equilibrium constants for binding. And it turns out that the error fraction can be written in terms of the ratio of these two affinities. Okay? But if we look at the error fraction in reality, so experimental numbers, is that this error fraction really ranges between very low numbers. And it's very improbable that these very low error fractions can be explained by this difference in affinities. Okay, so at the time when people realized that, they said, okay, so something else must be going on. That there might be another mechanism involved that explains why these error fractions are so low. Well, one part of many of these copying processes is, so one aspect of many of these processes where a template is being copied into a product, is that there is also energy being used. But it was never really understood what the purpose of this energy usage was. So, for instance, when the ribosome incorporates an amino acid that's bound to a tRNA, so first there is this complex of the ribosome bound to the mRNA that binds to the tRNA with the amino acid, and then something happens, there is energy being liberated. So GTP is hydrolyzed, and this energy that is stored into the protein, and the protein now is in an energized state. So the ribosome, this entire complex, is in an energized state, and then either A falls off, giving the energized molecule and going back, or the product is formed where you have the normal enzyme plus the correct product. Alternatively, so we have exactly the same route for the incorrect product. So everything works the same. So the difference of this scheme with the previous scheme is this hydrolysis, so this energy liberation and storage into an energized protein state. So only after this enzyme is no longer in this energized state, the product can be formed. So effectively what happens is that these energy hydrolysis reactions, right, they introduce a delay. And the consequence of that delay is that A and B, so the tRNA loaded with the amino acid, say, bind longer to the enzyme, so to E, before the catalytic event, so the formation of the product, occurs. Okay, so they need to bind to E for a longer time before the correct product is formed. Now, that means that during this extra time, B can fall off, and A can fall off. So that also, the effect of the delay is also, of course, that more A and B has fallen off. But since B falls off quicker, so has a higher, so the complex EB has a higher dissociation rate than the complex EA, what eventually happens due to this delay is that you accumulate this state rather than this state. So due to this delay you actually get more, so due to delay E star A over E star B increases. Okay, that actually means, this means that the error fraction, right, goes down. Yeah? Okay, so kinetic proofreading is, what it actually entails is that a delay is introduced due to the hydrolysis of energy, so of GTP in this particular case, but for other copying processes, other energy carriers, and this energizes the catalytic enzyme, and it delays its catalytic event, and during this delay more B will fall off the enzyme complexes than A, because the lifetime of A is longer than the lifetime of B. So in the end you accumulate more A than B, even though some A of course also falls off, but less A falls off than B. So the ratio of this increases while, so that means that more correct products are being formed due to the delay than incorrect products, and therefore the error fraction goes down. The system becomes better, so the precision increases. Okay. Due to, right, kinetic proofreading. Now that is the thing. That explains why energy is used in this process. It is not just simply dissipated, it's not wasted, it's really used to increase the precision. And that, I will stop here, and in the next lecture I will do the associated derivations.